Good afternoon, everyone. I'm Apurva Todkar, your trainer for today's session at the DE-CIX Academy. So, in this webinar, we will focus today on the BGP security, exploring how you can keep your network secure when using BGP. So, we'll go through a presentation with practical example and some best practices also. So, let's get started. So, what I'm talking about is, this is a type of a simple example network that you could see typically used at the DE-CIX Academy. So here we have AS6500 as a sample network, which is connected to the outside world via upstreams and peering. Like any other network, it's constantly under threat. So there are so many things happening on the internet, like the DDoS attacks, the DOS attacks, and many more. So today I'm just discussing about the attacks on the BGP. So this aren't always intentional, but sometimes they result from some sort of mistakes in the or the misconfigurations that you can have while configuring BGP. So, for instance, uh, private networks or private prefixes that shouldn't be in the global routing table can be received via BGP. So, in this example, also you can see we have a private network and a loopback IP address also received via BGP. So BGP itself isn't very permissive, but allowing the announcement of many incorrect routes. So as a network operator, it's your responsibility to actually ensure that it is not accepted or integrated into your routing table. So for example, as you can see in this diagram also, a /29 prefix is quite small and you would not likely want it and want to filter it out. So similarly, an autonomous system path containing a private AS number is also something that you want to avoid. So today's focus will be on protecting your routing infrastructure from such issues. So like I said, there's a loopback IP address, then there is a private network. So these all things are not actually good when we are doing routing over the internet. So let's see, protecting your routing infrastructure. So there's a standard document for this, an internet RFC, specifically RFC 7454. If you have never read an RFC before, so this is a great one that you can start off with. It's well written and it's also quite informative also. So it offers some practical advice on how to protect your network, including the best practices for filtering and the measures that you can take to safeguard your infrastructure. So today, I'll be sharing a few of these measures that's already been shared in the RFC 7454 and explaining them a bit in a detail in this webinar. So to begin with, what we call are some simple measures. So these are very easy to implement and maintain. And while they may offer some sort of limited protection, they are still valuable in safeguarding your network. So the first one that I would like to introduce, which many of you already might be familiar with, is the maximum prefix. So maximum prefix is a safety feature that allows BGP that helps protect your infrastructure. And I will tell you how the mechanism actually works. So imagine in this diagram, you are receiving 10 prefixes from your neighbor regularly. Everything is stable. And over a time, your neighbor might add a few more customers and suddenly you are getting 11 prefixes. Okay. As you can see in this animation also, you start receiving 11 prefixes or might as well start receiving 12 prefixes. But one day, all of a sudden, you start receiving 105 prefixes, then 1,800 prefixes, or even 3,45,000 prefixes also. So this is when an alarm should actually go off. Okay. So to prevent such issues, you can set a threshold of using maximum prefixes. So this threshold limits how many prefixes you are willing to accept from your neighbor. So if that number is exceeded, an action is also triggered accordingly. So most commonly, the BGP session is toned down to avoid such flooding your network with excessive routes. So the maximum prefix is a great feature to protect against misconfigured peers. So here's how it works in practice. So when a maximum prefix limit is exceeded, the router takes several actions. So first option being the tear down the session manually. So the BGP session actually shuts down when you unless you manually restart it. So this is actually not ideal especially during the off hours. So what preferable option that you can do is have a configured value like tear down the session with an auto restart functionality. So this session essentially shuts down the BGP but automatically restarts it after a set time. Like you can set for say 60 minutes, 1 hour, or 2 hours, depending upon your preference. And 2 hours is generally a standard practice and is a recommended option that you can set. So whenever any misconfigured peer does some sort of configuration or route filter changes done on their end, so he unintentionally also he might accidentally send you the entire routing table or misleading some of his LAN prefixes to your end, causing that prefix limit to go beyond the threshold. So in that case, this timer helps in to have a refresh, and after that particular interval, automatically the BGP session can come up. So another option we have is a warning only option in it. So it's just a sending a warning without shutting down the BGP session. So this best works if you have a 24/7 knock operation handling to address those immediate issues, and accordingly you can take action accordingly. So for best practices, you can set the maximum threshold to a safe number like 10 times the normal prefixes that you receive. So for example, I was receiving 10 prefixes from that neighbor, so I could set it to 100. So this protects you against major misconfigurations while receiving a full routing table also, like I suggested. So you can set a warning at 90% value to alert you before hitting that threshold. So let's talk about MD5 and session password for the TCP authentication. So this method is used to protect the BGP sessions from attacks, particularly crafted TCP reset packets. So here how it works. So imagine you have a BGP session and someone sends a malicious TCP reset packet to your router. So this packet can tear down your TCP session, so disrupting your BGP session. So by using MD5 or a session password, you can add an extra layer of protection that makes it harder for the attackers to send such packets. Okay, without authentication, your BGP session won't be established, keeping your session more secure with these unintended resets. So the solution here is to set a password on both the sides. The password is used to sign each TCP packet and that the sender sends, and the receiver checks the signature, and if it doesn't match, the packet is dropped without any notice. Okay, so even though MD5 isn't the best method today, but still it is considered to be secured enough. And a newer method is also implemented, like TCP authentication option also uses some sort of stronger hashing. But in modern terms, also many customers only prefer the MD5 authentication, and we ourselves also use the same method for connecting to our peers over the exchange. So a very important part of this is also to manage the passwords properly. So imagine a password is encrypted in your router and but it is not safely saved anywhere else. And in case you want to replace your router, so recovering that old passwords would be a big task for you. So you should use this method and some sort of a password management also to it, so that whenever you face such situations when you want to replace your router, you should have those passwords handy. Otherwise, if you don't have that, then you have to contact each and every peer for asking what was the password actually set with them. So next is the IP time to live security. So next method. So this next method is even simpler to set up and provides the same protection against the same type of attack that we already discussed. So, but without needing a password, here how it works. So BGP operates over TCP that you know, and the common way is to limit how far the BGP packets can travel is by setting the TTL value to 1. So this means that packet will only travel to your immediate neighbor. Okay. So however, it is even possible for someone to craft a packet with the TTL packet of exactly 1 when it reaches to the destination. So it can potentially cause a session reset also due to this. So while this isn't common actually in everyday use, but it's still not impossible. And you can still prevent this by setting the TTL value to 255 when sending any TCP packet to your particular neighbor in the BGP configuration process with that particular peer. So since every router or an IP node decreases its TTL value by 1, and if a receiver gets a packet with a TTL of 25, so the peer can also be 100% sure that it is received by its neighbor, directly connected neighbor only. So this method ensures that the packet is coming from the immediate neighbor, and there are no other routers that would have decreased the packet, the TTL value while coming along the way. So the TTL, IP TTL security in BGP works by making a BGP send packets with an initial TTL of 255, and the receiver then checks if the TTL is still 255 when it arrives, and if it's not, then the packet is silently discarded. And this method is very simple to set up. You just have to enable it while setting up with your peers. And there is no need for any complex password management like we have with the MD5. So, however, it does have to be configured on both sides. If one side is sending a TTL value of 1 and the other is with 255, it won't work properly. On both the ends, it has to be set with the same TTL value. And this is also defined in the RFC 5082 for your reference. Next point I want to talk about is about the BGP filtering. So think of it in this way: when you receive all the prefixes from your BGP upstream, your provider, they come very unsorted way, okay? And some of them might be unwanted also. So to manage this, you will create a blacklist to block these prefixes that you don't need. So similarly, if you have BGP customers, you may expect some certain prefixes from them only, which you allow through the whitelist or the allow list. So the key part in this intersection between this list, which represents the prefixes that you actually want to keep in your BGP table, and that is marked in the green area in this diagram. So this blacklist and the allow list may be small, but they are very helpful when you receive when you don't receive some undesired prefixes in your BGP table. So this helps to keep the BGP table clean and efficient. So let's first discuss about the block list, and you want to filter out in the BGP. So there are certain prefixes and AS paths that you should that should be excluded, and well, we will touch on the RPKI part also in the later on. So starting off with the prefix filtering. So here's what you don't want in your BGP table. Like for instance, as you can see here, there are some non-routable IPv4 prefixes that include the private IP address space, like the 10.0/8 network. Then you have the 192.168.0.0/16 networks that are actually not meant for the public routing. Also, you have some of the reserved IP address blocks like the 24.0.0/24 /4 subnet, which is used for the multicast address space. So you don't need that addresses in your normal BGP routing table also, and that also should be filtered out as well. Then you have the unallocated IPv6 space like the 2000 colon/3 that is also assigned for the global use. So you want to block everything outside of that subnet also, and just block everything else. So all of this unwanted prefixes uh, need to be organized in a list or a table depending upon your router's configuration. So for example, on Cisco routers, you can create a prefix list to filter this out. In this case, I have named the list as an IPv4 unwanted and applied to the filter inbound routes on the upstream provider. So this process helps to eliminate any unwanted prefixes that I mentioned before, referred to as the Martians from your BGP table. So the next filter to consider is the prefixes that are too small or too large. In BGP for IPv4, the typical prefix sizes that are accepted for routing ranges are between the /8 and /24. So anything smaller like /32 host route or anything larger is blocked actually. So because they are not suitable for the global routing table, which is already quite large. So for example, prefixes like /32 are already not desired in the global table, as they would unnecessarily be increasing those entries in the routing table, so which could further bloat the already massive table that we already have. So many years ago, providers agreed that anything smaller than the /24 should not be routable over the BGP global BGP table actually. And in case of IPv6, the accepted prefix sizes range from /19 to /48, while /19 is what commonly routed at the moment, and this could change in the future, but as of now, these sizes are what generally accepted in the IPv6 BGP routing also. And to enforce this limit, you can apply this to the access list or a prefix list on your router by setting up such filters and ensure that only prefixes within the accepted size range are allowed through the upstream provider. So more on the prefix filtering part will come. So another thing that you should filter out or which might not be obvious is the internet exchange point LAN prefixes. So you don't want to receive these LAN prefixes also, uh, or there are more specific routes via BGP. So let me explain why with an example. So take the network 80.81.196.61/21 that you can see over here, okay, which is peering with the other ISPs on the /21 range. Okay, so this network is a part of the DE-CIX Frankfurt LAN, and now imagine your router receives a more specific prefix for this network via BGP, like you can see here. That is the 80.81.192.0/24 from other interface. So since BGP prefers more specific prefixes, your router would choose the /24 prefix over the /21. Okay, so this should call all the BGP sessions using the /21 to fail, as your router would start sending the traffic to the more specific subnetwork that was received, possibly routed somewhere else. So instead of the correct IXP subnet which was already being received via the /21 subnet. So to avoid this, you should filter out the IXP LAN prefixes also being accepted via your other BGP sessions via your upstreams or your directly connected neighbors also. Okay, so this will ensure that your router doesn't mistakenly reroute the traffic and disrupt the BGP sessions. So if you're unsure what LAN prefixes are, you can find lists of them on the websites like PeeringDB as well. Okay, wherein additionally, if you're a customer of an IXP or an internet exchange point, you will know what these prefixes are and should configure a route filter to filter them out and never accept those XP LAN prefixes via BGP from any other source, as they could lead to misrouted traffic also. Similarly, you should also filter your customers' prefixes, like I said. So you don't want to accidentally route your customers' traffic to the wrong place also. So if you have a directly customer connected customer, and that customer is also connected to an internet exchange point. So sometimes what happens, those prefixes are learned via the internet exchange point also. So ideally, the traffic should go to your customer directly, can go the indirect path via the internet exchange point also. So that also you have to take care. So filter out those prefixes also towards the internet exchange point while filtering in the inbound route filter. So proper filtering on both IXP LAN prefixes and the customer prefixes is important for securing your network. Next up we have is the AS path filtering. So AS path filtering is another important step, even if the prefixes you receive are valid and the autonomous system path might be the problematic one. So for instance, if your own AS number appears in the path, the prefix is automatically filtered by your router. So however, you also need to filter out the private AS numbers and the reversed AS numbers. Okay. So to help with this, there is a page on the IANA where you can check which AS numbers are private. So the recommendation from the RFC is to filter these private AS numbers anywhere in the AS path that you receive. So not just the original AS. Private ASs shouldn't appear anywhere in the path. So for Cisco routers, you can use the regular expressions to filter the private AS numbers. Uh, like you can see here, though it might be a bit tricky, this regular expression filters out all the private ASN numbers, and other routers also like Juniper allows filtering based on the numerical values, numerical ranges, which can make it easier to manage. So for Cisco, it's often recommended to split the regular expressions into smaller chunks for ease of configuration. So when it comes to filtering BGP routes from customers, you generally need to use an allow list. Depending upon the size of your operation, managing this list can be also be challenging. So here are some ways how providers handle it. So one method is the manual updates that you can send via email to customers. Like some providers ask their customers to send. So one option is to manually update those via email. So some providers can ask to send certain updates via email. Like for instance, I'm a customer and I'm connected to an IXP or an upstream provider. Then I can tell them that these are my upcoming prefixes that I want to allow. So there's a manual intervention required wherein I allow those prefixes manually. And second option, that you can rely on a database like many larger ISPs, the tier one ISPs or the telcos or the transit. bandwidth providers or the internet exchange point like DE-CIX also rely on a database. So others like ask customers to maintain their networks on the public database like the RIPE, APNIC, and RADB. So you can automate those updates. So the approach you chose really depends upon the size and the complexity of your network. So you need to ensure whether you are filtering your bad routes to the customer, but you need to know how you want to implement this. So larger operations maybe using such automated systems. And so one common practice is to ask for a list of autonomous system numbers from your customers, like the AS macro that we ask to the customer, that is nothing but your AS set. So you can then use this information to automatically build some filters. So for example, at DE-CIX, we asked our customers to provide this AS set. Then what our route servers basically do, they expand this AS macro with the use of software, and based on that software, they create some filters for every customer. So this means that each customer, you need to maintain a specific list of prefixes and ASNs, which is complex, but it is actually necessary for the operations. And it's challenging, but it's manageable if you have some sort of a mechanism or a software to do it. So this helps to maintain the operations also pretty efficiently based upon the customer's prefixes according to their AS macro and their uh, source origin entries to the IRRs. So one last point also I wanted to cover is the RPKI, that is nothing but the resource public key infrastructure. But there's an entire webinar dedicated to it. So I'll just explain briefly about it here. So RPKI involves digitally signed route objects that network operators have to use or the resource holders can obtain from the RIS. RIS are your the uh, regional internet registries from where you get the actual IP resources from. So with RPKI, these resources holders can use public infrastructures to define their prefixes to be announced via BGP. So specifically, they can define an originating ASN, which is allowed to announce from a particular prefix and the maximum length of a prefix. So this information is contained in the route origin authorization, that is nothing but an ROA, a cryptographically secure way to inform the world that which ASN is allowed to announce which prefixes. So on the receiver side, this information can be validated using a software that communicates with your router, and this allows the router to either accept the signed prefixes or to reject the invalid ones. Okay, so this ensures more secure and accurate BGP routing decisions. So when validating these prefixes using RPKI, the software called as a validator checks for the prefix against the route origination, that is the ROS, and there are three possible outcomes for this check. The first one being the valid. The valid is the prefix which is covered at least in one ROA and the origin ASN is correct. And the prefix size is the within the acceptable range that is defined in your ROA. And the ROA is cryptographically signed confirming that the announcement is also legitimate. Then the second we have announcement type is of the unknown value. So this means that there is no ROA for the prefix. So most of the prefix that you see on the internet today fall in this category. So these announcements aren't signed but are not actually bad announcement, but they have no actually validated previously. Okay, but that can be used for announcement over the internet. And the third one is being the invalid one. So this occurs when an ROA exists, but the BGP announcement doesn't actually match with it. Like there can be an incorrect ASN or the prefix is wrong. So this invalid prefixes could be dropped by the network as they may represent some sort of a misconfiguration or a possible attack. So wrong prefixes are those which results in the invalid outcome during the RPKI validation process. So to wrap things up, let's briefly talk about the sending prefixes and the initiative by the Internet Society called as the Manners. Manners is nothing but the mutually agreed norms for routing security. So this idea behind the manners is essentially for promoting good behavior and cooperation in routing security. So this emphasizes for the following key principles. I'll show you. One being don't propagate any incorrect routing information. Okay, so we should ensure that the prefixes you send out via BGP are accurate, and what you filter out from your incoming route shouldn't be passed on to the others as well. So announce only what you are authorized to. So don't announce anything to your BGP neighbors that aren't supposed to. So be responsible whenever you share prefixes to your neighbors. The next we also have is to prevent the traffic with spoofed IP addresses, to implement such mechanisms to stop IP address spoofing also, which can lead to malicious activities in the network. Then you can facilitate some global communication, like if there's an issue with one of your neighboring ASNs or your BGP peering partners, you can communicate with them. So good coordination with them also helps to resolve the routing issues also quickly. And then you can validate your routing information also. So by following these practices also, you can help ensure that only valid routing information enters the global BGP routing table. So further enhancing security to the everyone who is accessing to the internet. So in essence, manners is promoting collaboration and responsibility among the network operators to make the internet routing more secure and reliable. So to conclude today's webinar on BGP security, here's a quick summary of the key points that we discussed. So implement some simple measures that we talked about. There are quick and easy steps that you can take to immediately resolve and improve your BGP security. So filtering incoming prefixes, block unwanted IP prefixes, including the private IP address space, and some non-routable IPs, and some reserved IP addresses that we discussed. Then uh, filter-based ASPass also to block routes that are coming from bad or private autonomous systems. Then you can validate the BGP customer announcements also to ensure that the BGP customers only announce the valid prefixes to the neighboring peers. Then outgoing filtering also. So only announce the valid prefixes to your BGP neighbors. And remember that if you don't allow bad routes in your network, so you also won't be propagating those bad routes out to the other networks. So these measures are straightforward but offer immediate protection for your BGP routers and sessions. Okay. So that wraps up the today's sessions on our BGP security. So I thank everyone for joining this session, and we are open up for any questions that our audience is having for this session. That was fairly straightforward topic for today on BGP security, and I believe many of the ISPs might be implementing few of those features like ESPOP access list, then BD MD5 authentication. Yeah. So any of the participants have any questions, they can post in the chat also. We are ready to answer them. How to apply RPKI in router? So basically what I said is RPKI is not specifically binded to the router, it's binded to the systems or the servers that are communicating with your routers. Okay, so we will have some sort of an RPKI session also in depth wherein we could discuss on how actually this functionality works, because many of the current CDNs and many of the internet exchange points have started implementing this. Like for you also know that Google also recently rolled out their filtering based upon RPKI also, but they have not strictly started to adhere those, but they are using it for the IRR validation also. So we could have that session only dedicated to RPKI in our upcoming session. So I believe there are no more questions from the audience, so we can wrap this session up. Thank you everyone for joining this session. We will see you in the next one. Thank you.
Thank you for watching.